So next topic chapter is spherical lens. What is a spherical lens? A lens is defined as a portion of a refracting medium. It is bordered by two curved surfaces as shown in the figures. It is bordered by two curved surfaces which have a common axis. When each surface forms part of a sphere, the lens is called a spherical lens. Various forms of spherical lens are possible, some having one plane surface as shown in the middle picture. This is acceptable because a plane surface can be thought of as part of a sphere of infinite radius. A convex lens causes convergence of incident light as shown in this figure, whereas a concave lens causes divergence of incident light as shown in this figure. The total divergence power of spherical lens depends on the divergence power of each surface and the thickness of the lens. Most of the lenses used in ophthalmology are thin lenses, and for a thin lens the thickness factor may be ignored. And the total power of a thin lens is the sum of the two surface powers. As shown in these figures, the total sum of a thin lens is the sum of the two surface powers. Refraction can be thought of as occurring at the principal plane of the lens, and in these lens diagrams only the principal plane is shown. In ray diagrams, the convex lens or concave lens, concave nature of thin lens is shown by the appropriate symbol at each end of the line that indicates the principal plane. Cardinal points of a lens. The point at which the principal plane and the principal axis intersect is called the principal point or nodal point. Here you can see this is represented by capital N. At this point, this is known as nodal point or principal point. Rays of light passing through the nodal point are undeviated. The first principal focus is represented by F1. It is the point of origin of rays which after refraction by the lens are parallel to the principal axis. The distance F1n is the first focal length represented by F1. Incident light, this is also shown in this picture. Incident light parallel to the principal axis is converged to or diverged from a second principal focus represented by F2. The distance F2in is the second focal length. By the sign convention, this F2 has a positive sign for a convex lens and F2 has a negative sign for concave lenses, and the lenses are designated by this second focal length f2. So the f2 has a positive sign for convex lens, so convex lenses are called plus lenses or converging lenses, and f2 has a negative sign for concave lenses, so concave lenses are also known as minus lenses or diverging lenses. Now if the medium on either side of the lens is the same, for example air, then f1 will be equal to f2. However, if the second medium differs from the first, for example in the case of contact lens, then f1 will not equal to f2. Thin lens formula: as with spherical mirrors, the position and nature of the image formed by a spherical lens depends on the position of the object, and a similar formula applies. This is the formula. In this formula, V is the distance of the image from the principal point. U is the distance of the object from the principal point, and f2 is the second focal length. So for an object in any position, the image can be constructed using two rays: a ray from the top of the object which passes through the principal point undeviated. This is the first ray. So the first ray passes through the principal point undeviated, and a second ray parallel to the principal axis. After refraction, passes through through the second principal focus. In case of convex lens, in case of concave lenses, it is away from the second principal focus. Away from the second principal focus. So in case the second ray after passes through parallel to the principal axis, after refraction it passed through the second focal length in case of convex lens. Here you can see in these three images. In case of concave lenses, after refraction it passes away from the second principal focus. Image formation by a thin convex lens. When the object is outside the first principal focus, the image will be real inverted and outside second principal focus. The object is at the first principal focus, the image will be virtual, erect, and at infinity. Third case, when the object inside the first principal focus, the image will be virtual, erect, magnified, further from the lens than the object. In case of convex lens, thin concave lens, in case of thin concave lens, real objects at any position produces a virtual, erect, and diminished image inside f2. Dioptric power of lenses, also known as the Virgin's power. The reciprocal of second focal length expressed in meters gives the Virgin's power of the lens in diopter. So here the F is the Virgin's power of the lens in diopter, and f2 is the second focal length in meter. Now here are the two examples. Suppose there is a converging lens of second focal length of 5 cm. So first convert it into meter. So a 5 cm will have 20 diopter power. But if we reduce the focal length, increase the focal length to 25 centimeter, then the power will decrease. So the lenses of shorter focal length are more powerful than lenses of longer focal length. Lenses of shorter focal length are more powerful than lenses of longer focal length. Therefore, the unit of lens power, the diopter, is based on the reciprocal of the second focal length. The reciprocal of the second focal length expressed in meters gives the Vergen's power of the lens in diopter, and this is the formula. Here F is the Vergen's power of the lens in diopters and F2 is the second focal length in meter. Now it is also possible to think of the other terms in the lens equation in a similar way. The reciprocal of the object and image distance in meters gives a dioptric value, which is a measure of the divergence of the rays between object or image and the lens. In other words, it is a measure of the degree of convergence or divergence of the rays in question. The concept of divergence is an important aid to the understanding of the optics of accommodation in presbyopia. Magnification formula. Linear magnification produced by a spherical lens can be calculated from this formula, where I is the image size divided by the object size, or from the distance of the image divided by a distance of the object from the principal plane. Now angular magnification. In ophthalmic practice, actual image and object size are of less importance than the angle subtended at the eye, because this angle subtended governs the retinal image size. Suppose we have object A, B, C, D, all subtend angle theta at the eye and produce a retinal image XY. They are all therefore of identical apparent size. Apparent size is given by the ratio of object or image distance, object or image size divided by its distance from the eye, which is of course tangent theta. When considering the eye, the angles encountered are small. For small angles, the value of tangent theta can be taken to be equal to the angle themselves. Now this figure shows that the object is the object and its infinitely distant image subtend the same angle at the lens and also at the eye. So apparent object size and apparent image size are the same. The angular magnification is unity. The object is at first principal focus of the magnifying glass or loop. The simple magnifying glass or the loop. When object approaches the eye, then it subtends a greater angle at the eye, and then the retinal image size increase. So the loop is a convex lens. It enables the eye to view the object at a much shorter distance than would be possible unaided. The magnifying power of the loop is F divided by 4, where F is the lens power in diopter. The commonly used 8 loop has a lens power of 32 diopter. Spherical lens decentration and prismatic effect. So when there is spherical lens decentration, prismatic effect is produced. So these are the rays of light, they incident upon a lens when on outside its axial zone. So this is outside the axial zone in case of convex lens. So these rays will be deviated toward the axis in case of convex lens. In case of concave lens, they are deviated away from the lenses. So this peripheral portion of the lens act as a prism because they deviate the light rays. The prismatic effect increases towards the periphery of the lens. So use of this non-axial portion of the lens to gain a prismatic effect is called lens decentration, and this is implied in spectacle where a prism is to be incorporated. On the other hand, when there is poor centration, suppose the center is towards the periphery, poor centration of spectacle, especially in high power lens, in patients with aphakia or high myopia, so there will be unwanted prismatic effect and it will cause spectacle intolerance, and this prismatic effect depends upon the prismatic power of the prism diopter, depend upon the lens power in diopter multiplied by decentration in centimeter. Now this increase in prismatic power of the peripheral parts is the mechanism of spherical aberration, ring scotoma, and jack-in-the-box effect. Jack-in-the-box effect, in which the object seems to jump in and out of the field of view as it moves out of and into the ring scotoma.